All right, so an outlet, a watershed outlet, is simply the location that a watershed drains towards. And so it can be any location on a stream that you're interested in, and the watershed is the contributing area upstream of it. So an outlet is just simply a point of concentration. As to the second question, why is the vast majority of fresh water on Earth not usable for humans? The reason for that is simply where the water is located. So we're not talking about salt water, although the majority of water on Earth is salt water. We're talking about the fresh water. You can't use fresh water that's at the ice cap or in a glacier. It's simply not mobile. It's not in a location we can get to it. And then even of the fresh water that's not at the glaciers and ice caps, if you look at water excluding that, consider the 30% of the water that's groundwater. We can use some of that, but some of it is so deep underneath the Earth's surface that it's not feasible for us to pump it out. And so probably only about half of the groundwater is within distance that we'd be able to pump it. And so that explains another part of it. Really, what I was expecting most students to say is just that the majority of the fresh water is tied up in glaciers and ice caps, but I'm just letting you know that also much of the groundwater is inaccessible, and if you consider surface water, ice and snow, we may be able to go scoop it up off of the ground somewhere in the case of snow, but it's just not, it's not feasible for us to collect water over a surface. We have to wait for it to melt and then concentrate in rivers and streams and lakes, and so it's really about where the water is located. Any questions about that? All right. Well, I handed out the notes during the quiz. Homework number 4 is due on Tuesday next week, and then the following Tuesday will be stage 2 of the project. Remember that I previously distributed the GIS files, and you should be able to import those into Google Earth Pro. Has anybody tried opening up shape files yet in Google Earth Pro? Not yet? Well, let me know if you're running into any issues with it, and we'll try and figure it out. We're going to be talking about climate today, and this is one of the chapters in your book that really shines. It's a great illustration of why I changed textbooks. It's really, chapter 3 in the textbook is fantastic, and I hope you'll take the opportunity to read it. What we're going to be covering today in one lecture is really just a quick glimpse of the information that's found in chapter 3. We're going to be talking about climate because remember that what drives the hydrologic process is the sun. And so a big part of what we're talking about today is solar radiation. The sun is what drives the evaporation of water, and it's the movement of the water through the atmosphere that explains a lot of variations in climate that are interesting from the hydrological standpoint. The overall big question of the course, you know, like what we're driving towards, what do you think the whole point of the course is, what we're trying to answer? Determine Q. That's right. I've nailed that. I've banged on that drum a couple of times. And so more specifically for an area that we're interested in, like a watershed, so it may be an urban watershed, meaning a parking lot or a housing development. As I was in Huntington, I actually went to a soccer game on Tuesday at the new, has anybody seen the new soccer field on 5th Avenue? They've got a parking lot there, and there's actually ponds all around the parking lot. They've done some of those BMPs that we talked about in class previously. It's kind of interesting to see that they've got some seeded areas that you can tell they're hoping the sheet flow off the parking lot will go to there. So, you know, the area of interest in the case of the new soccer complex would be the parking lot that they've got. What are the runoff characteristics? And the reason why we want to know the runoff characteristics is that in some cases we're interested just in the peak flow rate, maybe to size a pipe. But if it's sizing of a pond, then the runoff characteristics we're interested in is the flow rate over time. So the peak Q or the runoff hydrograph. And so some of the things that are going to contribute to the runoff characteristics would be the distribution of the rainfall. And we'll spend a couple of lectures talking all about rain. it will depend on infiltration. And so we'll spend several lectures talking about differences in soil type and ways that we can model the infiltration rate. And antecedent moisture means that sometimes during a storm event the soil is already saturated or partially saturated because of a rainfall event that happened previously. And so today, if it rains, probably we'll see more runoff than we did yesterday because it rained yesterday. And so if you have 3 days of rain and it's the same amount of rain every day, then the runoff will be getting worse by the 3rd day because of the antecedent moisture condition. So another one of the things that we'll talk about this semester is something that's known as abstractions. And that means processes that stand in the way between precipitation and runoff. So when there's evaporation off of a surface immediately after or during a storm event, and it's strange to think that there's evaporation happening during a storm. When it rains, there's still evaporation, even though it's very humid. But after a storm, there could be evaporation as the water is flowing over the surface that reduces the amount of runoff that we see. Interception, we'll talk about the processes that rainfall wetting trees or getting caught by buildings, and that reduces the amount of precipitation that leads to runoff. And surfaces like asphalt, concrete, even blades of grass have to become wet before there's a movement or flow of water. And so that's abstractions that we'll talk about. And then the fun stuff, once we learn a little bit about the concepts of hydrology, I think that the interesting thing is creating models. These are tools that try and predict what the amount of runoff is going to be for a certain amount of rainfall. And it's kind of exciting to create a prediction tool and then test that prediction tool against historical events. Like you can create a model that tries to predict what the hydrograph will look like. And then if you have data at that location, maybe it's a stream gauge, and then you also have a rain gauge in the same area, then you can see, you can compare your model and what the output of that prediction is to the actual observed conditions. And I've made some good models and I've made plenty of bad ones. And so creating a hydrologic model is a little bit of an art form as much as it is of a science. We'll spend just a little bit of time this semester talking about routing, which is the concept of delays that flow experiences as it travels from place to place. And how long it takes for water to flow over the surface, or how long it takes for water to go through a channel from maybe the top point in a watershed to the lower point in a watershed. And so we'll discuss routing, and then finally, what are the implications of all of these things? What sort of impact does runoff have on the economy? How can we avoid the damaging consequences of floods, and what kind of best practices are used to manage areas that are prone to floods? And there are actually flood insurance programs that are in the news a lot these days because of floods that have happened as a result of coastal storms. They're rebuilding a lot of areas in New Jersey and New York after Hurricane Sandy, and people are starting to ask the question of, does it make sense to build expensive homes right on the beach, where probably the storm that came through, the huge storm that came through last year, will be back again in 10 or 15 years, a storm that same size. It seems that the probability of big events like that is increasing as the temperature of the oceans increases, even slightly. So this is kind of the bird's eye view of the concepts that we'll cover through the rest of the semester. It's the big question of the course and some of the topics that play into answering that big question. All right. So the main focus of our lecture today is the climate, and specifically much of what we'll be discussing is solar radiation. Incoming solar radiation is what drives evaporation. both evaporation from free surfaces of water and also evaporation of soil moisture. So this diagram is showing a couple of things simultaneously. First of all, it's showing the chemical composition of the atmosphere and what different wavelengths are absorbed and what different wavelengths are able to pass through the Earth's atmosphere. And there's a reason why we're able to be outside, and because of the filtering effects of the gases in the atmosphere, will get sunburned, but we won't get totally fried to a crisp. Like if we were in outer space and we somehow didn't freeze, if we were exposed to the radiation that's coming off of the sun and didn't freeze and didn't suffocate, what would kill us would be the solar radiation, because the ultraviolet radiation and the high intensity of it, unless we are shielded by an atmosphere like we are, the oxygen and the ozone in the atmosphere shields us from the vast majority of ultraviolet radiation. And so that's, it's no coincidence that Earth is able to thrive on Earth because of the shielding from ultraviolet band. Now, the visible radiation carries heat, but it's not quite as damaging to cells. Infrared radiation is the band of energy that there's reflection back from the Earth. There's something called shortwave radiation and longwave radiation. And these short wavelengths, broadly speaking, are the energy that comes into our atmosphere has a short wavelength, and then the energy that is emitted from the Earth back into space is long-wave radiation. The sunshine comes in, it strikes the surface of the Earth, that which actually passes through the atmosphere, strikes the surface of the Earth's atmosphere stays at a relatively the same temperature, but during a daily cycle, the ground will get very warm and then it will cool, and at night, when there's no incoming solar radiation, much of the radiation that was absorbed during the day will be emitted. And you can sort of feel that effect if you walk next to a brick building in the evening. A brick that sun has been shining down on during the day, you can feel that it's sort of radiating heat. And the ground does that as well. It's not just brick. Anything that has thermal mass and that has the sun shining on it during the day is going to emit radiation. And the radiation that it emits is at a longer wavelength. And so this just sort of illustrates the different spectra that are emitted and received from the Earth. So how much of the radiation is kind of an interesting thing to break down. And here what they've done is, rather than use the actual units, the solar constant, there's 1367 watts per square meter that is coming from the sun, and that's what's shining down on the atmosphere, is 1367 watts per square meter. A small fraction of that actually makes its way into the Earth, and the reason why there is a difference is that for every incoming 100 units of solar radiation, you can see that a lot of it is reflected back into space even before making it to the surface of the Earth. And so there's reflection by clouds, backscattering by air, so that's the atmosphere protecting us from ultraviolet rays. There's reflection off the surface itself, reflection by surface. Now, an important part of the radiation that's reflected by the surface is at the poles. The ice caps at the North and South Pole are white in color, and they're able to more efficiently reflect sun. One of the interesting effects of climate change, and I don't know if you've ever seen movies that talk about climate change, but as the polar ice caps begin to melt more than they have before, there's this self-reinforcing pattern of there's less of the white cover that reflects radiation efficiently, and there's more open water, and that actually absorbs more of the radiation because of its dark color. It's able to more efficiently absorb and store energy, and so then the ocean heats up more than it did previously, and then that melts more of the ice and snow, And so it's kind of a feedback loop that it gets into, that there's less reflection there than there used to be and more of an accumulation of heat. So of what does finally make it to the surface, you can see the 50 units of radiation that makes it to the surface, then we can look at how that's emitted back to space. And the way that it's emitted back to space, there's net sensible heat flux, latent heat flux, and the difference between the sensible heat flux and the latent heat flux is just the radiation that, the wavelength that it's emitted back at. Some of the radiation that is emitted will be absorbed by the atmosphere and then reflected, transferred from the atmosphere to the to space rather than a direct emission from the surface to space. But this accounting of where the energy is pretty important when we get into trying to model evaporation, because evaporation of water, the really sophisticated models of evaporation, take into account the amount of solar radiation that you'll have in a certain area during a certain season, and it varies by how much cloud cover there is. And the really detailed models will take into account the temperature of the surface, the soil temperature, because the soil temperature and the difference between soil temperature and air temperature have an effect on how much of the heat flux is going back into the air, and the amount of radiation that's emitted has an impact on the amount of evaporation that's able to occur. This is just another way of looking at what we've already seen before, is just that solar radiation comes in at low wavelengths and it's emitted back to space in the longer wavelengths. So short wave radiation and long wave radiation. And if you look up radiation data online, there are quite a lot of places in the United States, about 300, that have solar radiation meters set up at weather stations. Probably more that aren't tied into the national network that's, the Department of Energy has a national network of solar radiation gauges, but they really only measure the shortwave radiation. The gauges that are there don't measure the amount of radiation that's being reflected back into space by the Earth. And so that's something that if you're doing modeling of evaporation, you kind of just have to empirically estimate how much radiation is going back out to space, because both incoming and outgoing radiation are required in the models that describe evaporation, but we really only have accurate estimates of the incoming solar radiation, not the outgoing terrestrial radiation. All right. In the previous slide, we saw this solar constant of 1367 watts per square meter. And so consider, what if this was a square meter? The sun is shining, and over from top to bottom, there's not going to be any variation in the solar constant. It's going to have the same incoming radiation, but because of the curvature of the Earth, what this is showing is the projection of that 1 meter of area that's normal to the sun at the poles is going to be spread out over a much larger area because of the curvature. And this variation in solar radiation intensity is due to the curvature of the Earth and the angle of incidence. And so it's not only just that there is a larger area that this radiation is spread out over, but also because of the angle that the sun is to the atmosphere, a greater fraction of it is able to be reflected. So when at the equator we have, if this represents 1 square meter, it's essentially projecting the solar radiation on the same 1 square meter, and a smaller fraction of it will be scattered off of the atmosphere because it's shining directly at a normal angle to the atmosphere. But down here at the poles, a very large fraction of it is scattered right off of the atmosphere, and the thickness of the atmosphere is larger relative to, the atmosphere has the same thickness all the way around, but the effective thickness, if you think about the path length of the radiation through the atmosphere, is larger, and so the light's more dim for that reason as well. There's a really interesting figure, this is taken from the text, that's showing the Earth's position relative to the Sun through different seasons. And it's kind of interesting. I'd never considered it before that the distance between the Earth and the Sun varies seasonally. And not by a lot, but you know, maybe 2%. The distance varies. Here you can see that on this side, when we have January, so that would be January 1st would be the northern hemisphere is in winter. NH means northern hemisphere, SH means southern hemisphere. You can see that it's a little bit closer to the Sun than during our spring and summer here in the northern hemisphere. It shows that during the different seasons the amount of sunlight per day varies, and there is no darkness at the South Pole during the winter solstice, but during the summer solstice, so this is the time when it's the longest day of the year, at the North Pole there's no darkness, and the South Pole there's no light. Has anybody been up to Alaska during the summer before and experienced that really long day? I've been up there once, and I was just in Anchorage, which isn't far enough north that it's continuous sunshine, but it was light after midnight, and then it got dim. It wasn't dark, it was dim. The sun was below the horizon, but it wasn't dark. And then the next morning, I went to the train station at 4 in the morning, and the sun was already up again. So it was pretty strange. It was dim for 3 hours, basically. And that was in early June, and so it wasn't quite yet to the summer solstice. It's a very strange thing. And then what was even more peculiar about that was I was in Anchorage, and as I was flying home, I left in the evening, and so it was, you know, about midnight, and it was getting dark. Not yet totally dark in Anchorage, but as we started to fly, it got totally dark. And then the route that we were traveling took us further north, and so there was a sunrise because we were going further north. And then as we started flying south again, the sun set again. And then when I finally landed in Detroit, the sun had risen once again. So it was sunset, sunrise, sunset, sunrise in one flight. Very unusual. My body didn't know what to think at that point. This is illustrating, this is a graph. This actually isn't a map. It seems like a map, but it's not. It's a representation of location and time, and how much solar radiation there is at any location as a function of space and time. And so these are the months along the bottom axis, January, February, March, April, May, June, July, and so on. And then this is showing at different latitudes. And so the equator, here's the South Pole, here's the North Pole. And here we can see that at the South Pole, for example, 0 means there's no solar radiation. And so they have a period from, including all of April, May, June, July, August, that there's no solar radiation. Now there may be a dim light in the sky, but it's not measurable. And if you take a radiometer outside, it's really amazing. I didn't quite notice this until I started playing around with the solar panels, that on a day like this, for example, it seems like there's a fair amount of light, but it may be a quarter of the solar radiation that we'd experience on a sunny day during the summer. Even though we can see a lot, it's not an appreciable amount of solar radiation in terms of growing things or trying to generate solar power. So then at the equator, you can see that it's relatively constant, the amount of solar radiation that there is over time. And you know, frankly, I'm not sure what these units are, 35, 30, 25, and so on, because the units of the overall incoming solar constant, 1367 watts per square meter. I need to look into more what the units of this are, but relatively speaking, I think that it's a linear scale, so we can tell that at, I think here where we're located, it's about around 50 degrees or so. You can see that there is, through the seasons, quite a bit of change in solar radiation through the seasons. All right. All of the impact of this variation in solar radiation is that when a land area warms, it causes thermals. And if you've ever learned much about gliders, you'll know that if you've got the land surface and the sun is shining down, it heats the land, and then there's the hot air rises. The surface gets warm, then the air at ground level warms up, and because the air at ground level warms up, it begins to rise, and there's sort of a convective effect where the rising air will cause movements. And what you can see here in this figure is that there are general circulation patterns that are a result of warmer temperatures at the equator, cooler temperatures at the poles, and this general circulation actually varies seasonally. And the reason why we have this general pattern of weather moving from the west to the east, that doesn't happen everywhere. We sort of take it for granted that a storm that they had yesterday in Ohio or Kentucky or Indiana is going to make its way towards the east coast. There are other places in the world where they have different patterns and where the weather may go from east towards west. And if you look down in South America, that's the case, that instead of having it go from west to east, it's the opposite direction, just because of, number one, the rotation of the Earth. There's the patterns that are induced by thermals as the hot air rises and the cool air sinks. And what you can see here is that if you look at the pole, the pattern is that here at the lower latitudes where the temperature is relatively warmer, the air rises, and then as the air gets towards the poles, it cools and begins to fall down. And so this circular loop here is because of changes in density of the air as the temperature varies because of different solar radiation amounts at different latitudes. Another thing that's driving the general circulation of air in the planet, and as air is moved around, so is moisture. But another thing that's driving it is that sea level actually the pressure, atmospheric pressure at sea level, varies seasonally. And this is showing what the typical pressure at sea level is in January, and it doesn't vary a lot. You can see that from place to place it may be as high as 10-20 millibars in one place, as low as about 1,000 millibars in another. These are sort of persistent averages over time, the pressure at sea level. But from January until July, in July the pressures are a little bit higher, as high as 1024, and the positions have shifted as well. So sea level pressures being different and also changing seasonally is another force that mixes the Earth's atmosphere. And so part of the reason why we see this general circulation patterns that we do is because there are differences in the atmospheric pressure from place to place, and the wind moves because of it. And this illustration shows that in the northern hemisphere, now it would be opposite of this in the southern hemisphere, but in the northern hemisphere where there are pockets of high pressure, then there's a clockwise rotation of wind. And where there are pockets of low pressure, there's a counterclockwise rotation of wind. And there's sort of a famous Simpsons where he's down in Australia. Has anybody seen that episode? and he's flushing the toilet and it goes the opposite direction, and so they build like a special pump that'll cause the toilet to flow the correct American way. That's just like a little gag they're doing. And so if you're in the northern hemisphere versus the southern hemisphere, there's I think it's called the Coriolis effect, a different rotational pattern, not only for high and low pressure atmospheric, but also apparently the way the toilet or the bathtub drains may vary, and the typical trend of it. And so some of the prediction that they're able to do for hurricanes, I think, is, you know, the typical patterns of hurricanes may be related to the typical, you know, high and low pressure rotation, clockwise versus counterclockwise. So what we've seen so far is that the movement of air through the atmosphere depends on temperature differences at different altitudes. And just flipping back to the global map, so temperature differences at different altitudes is not only the fact that as you get higher up in the atmosphere, the temperature decreases because of the adiabatic lapse rate. And we talked about this actually as far back as fluid mechanics, that with altitude and temperature, there's a relationship that the higher you go in altitude, that the temperature decreases. And the slope of this line is called the adiabatic lapse rate. And it's approximately 1 degree per 1 degree per 100 meters, I think it is. Approximately. So that as you go up through the atmosphere, if you've ever been in an airplane where it has a gauge on the side that says the outside air temperature, it's very cold outside, you know, like -30, -40 degrees Celsius as you're up at altitude in a plane, and it's because of the adiabatic lapse rate. And so part of the reason why there's temperature differences in the atmosphere is because of the adiabatic lapse rate, and it's also that as the air is circulated over the polar regions, it begins to cool and the density increases. So the bulk movement of air in the atmosphere is because of different temperatures at different altitudes, the rotation of the Earth, differences in heat and pressure changes with respect to location. And there's a term called Hadley circulation, and that is that in general, since we have warmer air at the equator, there's going to be more evaporation at the equator. And so it's warm, moist air at the equator, and it rises, travels towards the poles, and then it cools, becomes more dense, and as it cools, it becomes less able to hold the atmosphere, to hold the moisture that was trapped in it. So the solubility of water in air increases with temperature. So air is able to hold more moisture at a warmer temperature than at a cool temperature. And so as the air travels north, there's precipitation, the movement of precipitation from the equatorial locations towards the higher or lower latitudes, and precipitation occurs as the temperature decreases. Another trend that we have to be acquainted with is the Coriolis force. So the decreasing radius and increasing velocity as the air moves towards the poles. And so the thing to keep in mind is this is a cross-section of the Earth where this is the equator and these are the poles. And think about that if we look at it from above, what we've got is we've got air coming towards the pole from all directions. And so we've got a huge mass of air from around the equator all converging in the same location. And as it comes towards the same location, then the velocity increases because you've got a large mass of air, and it's kind of like a pipe, a smaller cross-sectional area for the pipe. The velocity is increasing, and that's partly why the winds are so extreme at the poles. If you've ever seen one of those penguin movies, you've seen the penguins standing there holding the eggs, and it's, you know, like 100, 200 mile an hour winds, and they're just standing there for months at a time. They have really extreme winds, and it's partly because of the velocity increasing as the radius decreases. All of that air that is moving towards the poles accelerates the closer it gets to the pole. As the air moves, so does moisture. And this graph, in some ways, is a throwback to our last lecture, where we were talking about the relative quantities of moisture in different places. This is probably more numerically rigorous than the conceptual diagrams we were looking at in the last class period. This is showing how much water is in different places. And we've seen that in terms of percents, but this is more absolute here. So there's a certain amount of water in the oceans, a certain amount of water in the ground. You can see how much water is stored in the atmosphere at any time. The fluxes, these movements that are shown, are on an annual basis. And so where it's a store of water, a stock that's enclosed by a box, that's meant as just at any one time how much water is in a certain place. So right now, for example, there would be 16,500 units of moisture, of water in soil moisture. And then the movement between soil moisture and biomass, that would be trees and plants, there would be 71,000 units of movement during a one-year period. Why do you suppose that there is a negligible amount of movement of moisture from the atmosphere to rivers? Why do they say that is negligible? What's to explain that? Okay, that's partly it. But it's saying that when it rains and gets into rivers directly, it's negligible. Right. That's right. It's just that a lot of these things have to do with surface area. And so if you think about the movement of water between the atmosphere and oceans, look at the relative differences there. It's showing that there is more movement of water from the ocean to the atmosphere than gets back onto it. This 485,000 is rain right directly onto the ocean. And this is showing that there's more evaporation from the ocean than there is rainfall directly onto the ocean. So does that mean that the ocean levels get lower and lower over time if there's more evaporation than there is rainfall? And think about the mass balance of that. If we say accumulation is in minus out, it looks like we have more going out of the ocean by evaporation than we have going in. There's runoff as well. So the difference is the runoff from the land, it's flows from rivers and groundwater flow. All of these make up the balance so that there's a steady state of no accumulation, no loss. So I thought that this is an interesting figure because it shows the relative quantities in any one location and then also the movement on an annual basis. So this 116,000 is the movement. It's basically infiltration. Some of it gets into the soil moisture. The soil moisture is also the loss of soil moisture to biomass is roots of trees and plants sucking up soil moisture, and then there's evaporation. Why do you suppose that on an annual basis they're the same, that biomass takes up as much as it loses? If we look over the very long term, that may not be true because they say that rainforests are being cut down and there's less vegetation in a lot of places than there has been in the past. So I mean, strictly speaking, in any one year, there may be slightly less uptake than there is emission. This is assuming that the amount of vegetated area stays constant from year to year. There's evidence that that may not be the case. Okay, so these precipitation is represented by this. Precipitation is represented here, and precipitation isn't constant all over the Earth's surface. There's more precipitation at the equator than there is at the poles. Why? Why do you suppose that there's more precipitation at the equator than at the higher latitudes? All right. Warm air holds more moisture. There's more solar radiation. Remember, at the beginning of the lecture, we were looking at figures that showed not only is there less reflection at the equator, but there's just that same 1 square meter of solar radiation is cast over the 1 square meter of soil. So more radiation, warmer temperatures, it allows greater evaporation, and in locations where there's lots of evaporation, there will be a lot of precipitation. And this is in units of millimeters per year. Anybody know what our precipitation is in millimeters per year in Huntington? I have to do the conversion myself. I know what it is in inches, but not millimeters. What we've got is about 40 inches per year here, so 40 times 25. It's approximately 1,000 millimeters per year, and there are places where the precipitation would be nearly double that. And I think it's even greater in places where maybe it's along a mountainside, like in Hawaii. I was looking at precipitation variation in Hawaii just last night. I got a guidebook for Hawaii, and one of the pages on the guidebook was showing how precipitation varies from the mountain down to one edge of the island, gets as little as, I think it was saying 10 inches per year, and then there was one part of the mountain that got, what was it saying, like 200 inches per year, it might have been, where it rains every day at the same time. This figure is showing that in certain parts on the Earth, they have a monsoon season. I think India is kind of, oh no, that's actually the next figure. This is just the amounts. It's not seasonal precipitation regimes shows the monsoon. So we'll just look at amounts first. So this is showing the, coastal areas like California have really high amounts of precipitation, as do in South America. What's to account for the really high precipitation here is the fact that it's near the equator. It's also mountainous. The Andes Mountains leads to a lot of precipitation. Again, here in Africa, close to the equator, close to the ocean, lots of precipitation. But at low latitudes, there can still be deserts. Here in the Sahara Desert, it's close enough to the equator that you might expect there to be plenty of precipitation because it's warm air and it's coastal, and yet it's still very dry. And I don't know all the reasons for that, but I think it might have to do with the air patterns and whether the air is moving from the ocean towards the land or whether the air is moving from inland and out towards the ocean. So if we go back to the typical wind patterns here, looks like this is just really showing the Americas and North and South America. This isn't quite so much showing what's going on in Africa. You can see there's a wind pattern that is from northeast towards southwest, and if that same pattern held true over Africa, that might explain why it's so dry here. As if the wind is coming from Asia, then that's not from the warm, moist direction where all the precipitation is. All right, so this is the slide that I was referring to earlier that illustrates locations that have monsoon seasons. There are different types of precipitation. Even in the United States, there are places that have a summer maximum where the highest rainfall during the year can be expected during the summer in locations that are indicated with summer maximum. I'm not sure how we're supposed to distinguish these two. Dots versus dots. What's that?
Spring and summer maximum.
Yeah, they kind of do, don't they? In the textbook, maybe there's a shading there that wasn't distinguished when I scanned it. I think that this is maybe supposed to be a little bit darker than that. But well, we experience in West Virginia, it may rain any month of the year. I mean, there are certainly periods where it rains more than others, but there are some places here with the cross-hatched areas where they have a marked dry season and then a wet season that's just most of the rain happens during a certain monsoon season, and it may vary on whether it's in the winter or in the spring. There are some places where they have a winter maximum, like down on the south coast of Australia. They have a marked dry season, and yet it's wet predominantly during the winter months. Here in India, it may be spring or summer. We can't tell because it's cross-hatched light. But here in the United States, we don't really have a lot of areas that have a marked dry season. It looks like just maybe in parts of Colorado, Idaho, Wyoming, that we have a very narrow slice of the country with this marked dry season. For the most part, we have locations that have the possibility of rain at any season. Now, the types of plants that grow in a climate will definitely be affected by this. And so part of the reason why when you go to a different biome, as it's called, a different location has a different climate, different temperatures. Not only precipitation amounts may be different, but the temporal distribution of rainfall, when it gets it during the seasons. And so there are places in India that have the same amount of precipitation as West Virginia on an annual basis, but they don't have, and they may even have the same kinds of soils, but there wouldn't be the same types of trees because different trees tolerate a dry season better than the types of trees we have here in West Virginia that may not be as tolerant of a dry season year after year after year. And this figure illustrates the amount of water that evaporates in a single day. So if you break the Earth up into a grid, and I think that each one of these blocks represents approximately 5 degrees of latitude and longitude. So, a spot that's over, I think this is Brazil mostly. This is the water that evaporated in one day, and then they track the precipitation over 2 months. And where does that precipitation end up over a 2-month period? And so the movement of that water over a very, very large area illustrates that, number one, the wind is quite effective at distributing precipitation, and also that if there's a small change, a localized change in temperature in one area, then that change in temperature, even if it's just localized, that a change occurs, it can have an impact on a much larger region. And so there are places in China where, we watched this in the movie last time, where there's been desertification and environmental damage, and they say that deserts are sort of continuing to intrude in some areas in China. The Laos area that we were looking at has been partially restored, but desertification of the Gobi Desert is the march of the Gobi Desert towards the east to parts of China that aren't yet desertified is a risk, because if this square that used to be forested becomes desertified, then you can see that it has an impact over a much larger area. And that's sort of why, if you've heard of El Nino and La Nina, it's cyclical patterns of relatively warmer and cooler temperatures. El Nino is when there's a warm temperature in the Pacific Ocean, and it has an impact over a huge area. California feels the brunt of it in the United States. And La Nina is when it's unusually cool temperatures, and it's just in a very certain sort of an isolated region of the Pacific Ocean that there's these unusually warm or cool temperatures, and the effect that it has is over a much larger area. And this sort of illustrates that that's possible. This is showing for another location. This is over Thailand and Vietnam, when there was a period of 1 day of evaporation in black, and then tracking that 2 months of precipitation, where the water went to. Now, I'm not sure how this information was derived. I mean, to actually physically measure that, they need to somehow seed the moisture with radioactive isotopes or something. I think that they probably modeled and tracked the movement of the moisture using probably satellites and tracking the wind. And I imagine that this is an estimation and measurements, like remote sensing measurements, rather than they had some way of actually labeling the H2O molecules and tracing them where they went. But it's an interesting illustration nonetheless. This figure illustrates different biomes, different types of climates that exist, and it shows the range of precipitation and annual temperatures that can sustain the biome. A tropical rainforest, for example, can only exist in places that have not only very high precipitation, precipitations between 250 centimeters to 450 centimeters, but also there has to be a certain range of temperatures between 20 and 30 degrees as a mean annual temperature, so averaging the temperature over the entire year. On the other hand, taiga, which is the biome of northern Russia, Siberia is described as having a taiga climate. That has a mean annual temperature anywhere between -5 to maybe as high as 3 degrees Celsius, and a certain range of precipitation. And so the different types of vegetative cover that you'll see in different parts of the world are affected by the mean annual temperatures and also the mean annual precipitation. Okay. And I think another part of the reason why there can be such a wide spread in some cases, why isn't it a narrower range, is that there are other factors about what supports the biome, like differences in soil types, differences in probably the wind patterns also have an effect on how wide a particular biome is. So it's interesting to think about the different vegetative cover and different types of plants that exist throughout the world, and this kind of illustrates why that may be. There are other factors that help to explain the atmospheric variation in precipitation and variations in pressure. Like why are there differences in atmospheric pressure, as we saw in that earlier graph. And it partly has to do with the fact that there is an uneven distribution of ocean and land. And in the northern hemisphere especially, there's much more of the Earth's surface is in the northern hemisphere than in the southern hemisphere. The percentage of land is vastly exceeded in the northern hemisphere than in the southern hemisphere. And because of that, there is the effect that the land heats and cools more quickly than water, and so there are a lot more of the thermal effects in the northern hemisphere than in the southern hemisphere. Thermal equator is a term that's talking about where the temperature is the greatest on the globe. And the equator itself is always at 0 degrees latitude, but when the Earth rotates so that the northern hemisphere is facing the sun, then it heats the northern hemisphere more, and so that the average highest temperature may be north of the actual equator, and that's called the thermal equator, the location where the temperature is the greatest. And so we already talked about monsoon variations and how there may be an extended dry period in certain parts of the Earth, and the accumulation of warm water in the Pacific Ocean that leads to El Nino, the accumulation of warm bodies of water. El Nino is where in the Pacific Ocean there will be unusually warm water, and then there's a lot of extra evaporation, and that also affects the wind patterns, and they experience really high wildfire potential in California during El Nino because it's so much more windy there. And one of the things that causes out-of-control wildfires is not only warmer temperatures and drier conditions in California, but also when it's windy, that's sort of what helps the wildfires to move quickly and get out of control. So, all right. That's it for Chapter 3, talking about climate. Let's just take one last look at some of these announcements before we finish for today. Remember, homework 4 is due on Tuesday, and that included a book question and then a few questions that were on the handout that I gave you. And what I hope you'll do is start exploring the pipe data that's there and making a list, either working individually or with the partner, making a list of what else you need to know. And so it should be in the form of a conceptual drawing. You can get an 11 by 17 piece of paper, I think, and that would be large enough to sketch each pipe in the network for the project area and annotate the pipe diameter, the elevation of the inlet, the elevation of the outlet, if you have that information. And where the information isn't available, it says in the handout that you should sort of highlight where the missing data is, and maybe even with a yellow highlighter. Just highlight the fact that at this end of the pipe the outlet elevation is unknown. Or if you have a pipe in the network where it doesn't say the material of it, maybe it's concrete for much of the rest of the network, but one particular pipe doesn't have the material specified. Just identify all the gaps in the data, and then I'll compare what each of the groups have found. Hopefully there's pretty good agreement of where the gaps in the data are, and I'll get in touch with HSB and see if they can provide any of the missing data. So that's what you're working towards on stage 2 of the project. All right, well, I will